Okay, so it's kind of all well and good talking about the theory behind tail recursion, but just like for the basic case, the only way we can get a real grasp on this is by implementing our recursive function, our tail recursive function. So let's write a tail recursive implementation of the factorial function. So we're going to make a main file. We're going to open it, and we're going to include our standard input-output library. We're going to make a main function, have it return 0, and we're going to write, this time we're going to say it's going to return an integer, but we're going to call it fact_tail because it's the tail recursive implementation, and it's going to take an integer n and another integer a. Okay, and that's just the prototype, so I'm going to implement it just here. Okay, and let's write how we're going to test this first. So we're going to first read data, or prompt user for input, and we are going to compute the factorial, and finally we're going to report the factorial. Okay, so how do we prompt for input? Well, again, we use printf, so we write a message, we say please enter a positive integer, and we don't mean strictly positive, we mean we can include 0 as well. We're going to say scanf %d, and we're going to enter, we're going to store it in a variable called n, but here we're going to just put an integer n here for the one we're going to store. And next we're going to compute the factorial, so we're going to say answer is equal to fact tail of n, which we've read from the user, and 1. Okay, very important that we have the 1 there. What we're going to do is we're going to do something about that in a moment, but we're going to leave it as it is just now, and we will execute it like this, but we'll have something more to say about how to clean this up in just a moment. And finally, we're going to report it. We're going to say print. Well, firstly, we want it to return a sentinel value if we have bad input. So we're going to say if the answer is equal to -1, and the other case is otherwise, we're going to just do what we think we're going to do. But if it's -1, we're going to print an error message. Error, can't evaluate the factorial of a negative number. And we'll terminate that line with a new line character. And otherwise, we're going to say that the answer factorial is equal to the answer. So here that's got to be n, and that's got to be answer, because n is going to be put into this format character, and answer is going to be put into this format character. Okay. Very good. So we've written our test code. So now we just need to actually implement it. Well, the implementation, we know that there's kind of three things to do. We say if n is negative, so if it's less than 0, we return our sentinel value -1. We say if n is equal to 1 or n is equal to n is equal to 0 or 1, then we return 1, and otherwise, so we say else, and then we just finally say else, we are going to return our we're going to make a tail recursive call. And what's a tail recursive call? A tail recursive call is a recursive call that does no work. Okay, so you're just asking for the return value of the function and you're not doing anything to it. So in particular, I'm not going to be multiplying by n. I'm going to be making that tail recursive computation that we talked about before. So here we say if n is less than 0, we're going to return -1. And we're just going to do things a little differently here. We're going to say if, else if n is less than 2, if n is less than 2. So that subsumes all the values 0 and 1, because here we've already taken care of the case where n goes all the way from minus infinity, or, well, you know, the smallest machine representable integer, all the way up to, but not including 0, so up to -1. Well, here, because we've already ruled out those values, it's completely fine to just say, well, now I want 0, now I want 1, but I don't want 2. Okay, and here we're going to say, in that case, we're just going to return 1. And finally, we're just going to say else. We're going to say else. We're going to make our tail recursive call, so we're going to return fact underscore tail, and what we're going to put? We're going to put n minus 1 to signify that we are reducing our work, and we're going to say n times a for the actual calculation to update our stored value. Now let's actually compile it. So we're going to say gcc o fact tail test main.c, and again I anticipate maybe I've made a mistake. Aha, there we go. So line 13, and again what it was I didn't have a variable answer. So you can see here answer undeclared. So I'm going to say yanking paste answer here. Hopefully that will compile. Oh, and I've got something else on line 29. So I didn't put a semicolon. There we go. So let's try to test it. And we're going to test it with -1. And we got an error message. We're going to test it with -2. We got an error message. Test it with -77. And we got the same error message. Now we're going to just test it with some values. So we'll test it with 0, and again we got 1. We'll test it with 1, and we got 1. And we're going to test it with 2. Ooh, so something's not quite right here. So let's look back to our recursive call. Let's just check what we get with 3. Yep, so something's clearly not right right here. So what it is, the problem is that I'm having my function recall return 1 and not a. I'm having it return 1 and not a. So I should have looked more carefully at my tail recursive definition. So let's compile it again. So gcc o fact tail test main.c. I'm going to call it again. -1 seems to have a good answer. -2 seems to have a good answer. -64 seems to have a good answer. Let's try it for 1. We get 1. Let's try it for 2. We get 2. Ooh, and again, let's see. So if n, let's see here. So again, we have to be careful. So if n is equal to, oh no, that's fine. Sorry, excuse me, please excuse me, that's fine. That's absolutely fine. So we have 0, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. Very good. Let's see. We have 4 factorial is 4. We have 5 factorial is 5. And we have 6 factorial is 720. And one more time, we're going to have, let's say, let's try it for 7 factorial, which I think, which was 5040. Okay. Now, I said we were going to make this a little prettier. I said we were going to kind of tidy this up because this is not a nice way to call a factorial. We don't want this kind of superfluous argument that doesn't make for very tidy code. So what I'm going to do is I'm going to define a wrapper function. I'm going to call it int fact, and I'm going to give it one integer argument. I'm going to paste it here and just implement it at the bottom just under factail. So here I've got the prototype, and at the bottom I've got the definition. So what am I going to put in the definition? Well, what I'm going to have is I'm going to just have it return factail of n and 1, right? So I'm going to have it do the nasty work for us. We're going to compile it just to check that I've not had any typos. Very good. Now, in the actual code, I'm going to replace that with not factail of n and 1, but fact of n. And let's compile it again. Everyone seems to be happy. So let's check. So we're going to have -1, error, -2, error, -453, error. Let's try 0 factorial, 1, 1 factorial, 1, 2 factorial, 2, 4 factorial, 24, 6 factorial, 720, and 7 factorial, 5040. So it seems that we haven't made an error in wrapping our tail recursive definition of factorial. Note the overhead here is just one more function call, but two things. One, listen, when you are computing factorials of very large numbers, of course, please understand there's going to be a much faster version of this function probably in the C standard library, so you wouldn't use this definition anyway. But usually, if your algorithm is recursive, if you've spent the time to design a recursive algorithm, it's because you intend to evaluate a lot of data. So if you're going to be performing a lot of calculations, like say, input of size 10,000, what's one extra function call between friends? So really the idea here is that this extra function call, it kind of doesn't matter. Moreover, I suspect you probably wouldn't have to put the optimization up even past 1 for the compiler to know to optimize this out, right? It would probably just, the compiler would probably just treat this as an inline function, I suspect. I have no reason to know that. I freely admit that I have not spent much time perusing the C standard, but my understanding is that things like these, I know for a fact that C++ would optimize that out. I know that to be, I utterly know that to be a fact. But in C, I believe that something like this would be optimized out. Please feel free to correct me in the comments in case I've just spewed abject nonsense. But the bottom line is, you have two situations. One, you've added an extra function call. Okay, who cares? I'm computing the factorial of 10,000, so I've done 10,000. I've updated my stack frame 10,000 times, and then I've made another function call. Who cares, right? So you've added a pop, you've added a push and a pop. Essentially, is what you've done. Even more, it's kind of like the compilers these days tend to be really quite good, so it will probably get optimized out anyway. So this teeny tiny thing you're worrying about is not even going to be there in your final machine code.